Hi viewers, and welcome to my latest video on understanding maths hack. The internet is awash with maths tips and tricks and hacks for people to use in calculation. But if anybody knows anything about me and knows about what I believe in for maths education, I think kids should not only be able to do math, but also understand math. And today I'm going to look at a wonderful trick that's taught lots and lots of places. It's finger math. And if you've not come across finger maths before, then finger maths is a lovely trick, particularly for the times tables 6 through 9. It helps with calculating the times tables 6 through 9. And it goes a little something like this. You have your two hands facing you, palms up, like that. So you've got your 10 fingers. And you can see it, I've done it on the diagram here. From left to right on your left hand, you number those digits 6, 7, 8, 9, and 10. So you're skipping 1 to 5. And on your right hand, you do the same thing. You number back from your thumb, 6, 7, 8, 9, and 10. And then, so we're trying to do a calculation that relates to one of the times tables 6 through 9. Let's say we're trying to do 7 times 9, and we can't remember what 7 times 9 is. Well, the way the finger trick works is there's simply, you fold down the fingers up to 7 on your left hand. So we're doing 7 times 9. So you fold down the fingers up to 7 on your left hand, which would be your thumb and your first index finger there. And then you fold down the fingers up to 9 on your right hand. Those 6, 7, 8, and 9. So that would be the 4 fingers on your right hand, leaving just your little pinky sticking out. And then to work out the answer to 7 times 9, you first look at your folded fingers and you say, right, how many folded fingers do I have? Well, I have 2 here and 4 here. So that is 6 folded fingers. And we just add those two numbers together and that goes into our tens plate. And then we look at how many fingers we've got left raised across both hands. And we don't add those because I know what you're thinking, but you've got 4 fingers raised and 3 add 1 is 4. We don't add those. We multiply those. So we've got 3 fingers on our left hand, 1 finger on our right hand. And so we're going to multiply those together. 3 times 1 is 3. And you can see we get the answer 63. And that doesn't just work for the 9 times table because the 9 times table is quite special. It works for all times tables. Let's say we were going to do 7 times 8, which just means we're going to leave this 1 extra finger up. If we're going to do 7 times 8, then again, folding down 2 fingers on our left hand, but now only 3 fingers on our right hand, 6, 7, and 8. They go down. And that means we've got 5 fingers folded down altogether. And then if we look at how many fingers we've got standing, we've still got raised on our 2 hands. We've got 3 over here still, but then 2 over here, and 3 times 2 is 6. And so we've got 56, which is, of course, 7 times 8. And it's a lovely trick. For those times tables that are a little bit trickier sometimes for kids, like your 6, 7, 8 times table, it's a wonderful, lovely trick. But why does it work? Well, interestingly, we can prove that this works algebraically, and I'm going to show you that first. But for me, the algebraic proof although it shows that it works, it doesn't really give us a sense of why it works. And I'm going to show you a lovely diagram a little bit afterward that shows you why it works. But let's start with the algebraic proof. We're going to define some variables for our algebra. So we're going to say, right, well, let's first of all say that what we're trying to work out is x times y. We're trying to work out x times y, where x is some number between 6 and 9, and y is some number between 6 and 9. And then we're going to define a here to be the number of fingers that we fold down on our left hand. Yeah, so in the case of both of these calculations, it was the 2 fingers. We're not going to get into the whole is the thumb a finger debate, by the way. It's the 2 fingers. Okay, so the 2 there. And similarly, over here, we're going to define a variable b for our right hand for how many fingers we fold down on our right hand. So in the case of 7 times 9, it was 4 fingers. In the case of 7 times 8, it's 3 fingers. And then what we're going to do is we're going to define our variables for those fingers that we left standing. So over here, the number of fingers on our left hand that we leave raised, C, and the number of fingers that we leave raised on our right hand, D. So we have these 4 variables. And if we track what happens to those 4 variables when we do this, we'll see that the product xy pops out very nicely. So what we did for both of these calculations and for every other calculation is we said, okay, we're going to do A plus B, the folded fingers on our left hand and the folded fingers on our right hand. So A plus B. And we're multiplying that by 10 because that forms our tens digit. Yeah? In both cases, it was 7. It was 5 or 6 because it was 7 over here, but it was either, so it was 2 fingers over here, but it was either 3 or 4 fingers over here. But that forms our tens place. So we're multiplying that by 10 to give our tens place. And then what did we do with our raised fingers, our C and our D? Well, we multiplied those together, so C times D, or just CD, and that goes into our units place. And that's the trick, basically. Yeah? Add together your folded fingers, they go in your tens place, 6 or 5. Multiply together your raised fingers, that goes in the units place. 3 times 1 or 3 times 2. But let's look at how these variables A, B, C, D relate to X and Y. If we look at A first of all, well, A was 7 in both cases here. But what we can see is that even if A wasn't 7, if it was 8 or if it was 9, then the number of fingers we were folding is the number we're multiplying, subtract 5. Because we're starting our numbering from 6, we're ignoring 1, 2, 3, 4, and 5. The number of fingers we fold down is always going to be 5 less than the first number in our product. So this value of A here, I'm going to leave my 10 in, but this value of A is actually X minus 5. And similarly on this side, this value of B is actually Y minus 5. And so if we're folding down 3 fingers for the number 8, because 8 is the second number in our multiplication, well, 3 is 5 less than 8. And if we're folding down 2 fingers for 7, 2 is 5 less than 7. It's always 5 less than the number that we want to multiply by because we're starting our finger numbering from 6. So this is actually our tens digit in terms of X and Y. And now let's look at C and D. Well, C is the number of fingers we leave raised. But obviously, C is also the number that has to add to A to make 5. I have 5 fingers on each hand. A and C are, if A is my folded fingers, C are my raised fingers, and those 2 numbers together have to add up to 5. So, in order to get C in terms of X, I need to think about this X minus 5 and think, what do I need to add to that in order to make it into 5? Well, I've got to do a couple of things. First of all, I've got to get rid of this X, because I don't want X in my 5. And then I've got to turn this negative 5 into positive 5. And how do I turn negative 5 into positive 5? I add 10. So this C is 10 minus X. And if you check it with the numbers, you'll see that it's true. Look, C was 3, which is 10 minus 7. When we had 7 times 8, D was 2, which is 10 minus 8. And when we had 7 times 9, D was 1, which is 10 minus 9. Okay, so it does work. And so similarly over here with D, we're going to have D as 10 minus Y. And now if we tidy this up a little bit and expand these things, I'm going to tidy this up and say, just treat that as X plus Y minus 10. And then expand these brackets. We end up with 10X plus 10Y minus 100, because minus 5, negative 5, negative 10, times 10, negative 100, plus 10 times 10 is 100, minus 10X, minus 10Y, and then because negative times negative is positive, plus XY. And we can immediately see here that a load of this stuff is going to cancel out. That 10X minus 10X, that 10Y minus 10Y, that positive 100 minus 100. And what we're left with is just our XY, which is the product of the 2 things we were trying to find. And that's great. The algebra proves that that process will always work, provided x and y are numbers between 6 and 9. Fantastic. Okay, so it doesn't really explain why it works. It just proves that it does. Let's see if we can dig a little deeper and get into why this actually works. And to show you that, I'm going to draw you a lovely diagram of an area model for this calculation. So this is my area. This length here is x. I want you to imagine what's like an axis, starting at 0, going to x. This length here is x. This length here is y. And so what we're going to do is we're going to break this area up. Okay? Starting with our A and B. So A is, A is the number that we add to 5 to make x. So I've marked a 5 on here, and I'm also going to mark a 5 on here and draw in that area. And that A is the difference between x and 5. Yeah, x minus 5 is A. We saw that before. Okay, and similarly over here, we've got B. And so now if we just look at this part of what we've drawn, we've got A times 5, which is 5A, and B times 5, which is 5B, and then this rectangle here is A times B, so that's AB. And that's a good start. But I need 10A and 10B. If you imagine this expanded, you'd have 10A and 10B. I need 10A and 10B, or 10 lots of A plus B, and at the minute I've only got 5 lots of A plus B. So where am I going to get the rest? Well, I'm going to take this space that I haven't labeled yet, and I'm going to come down A below the 5. And similarly here, I'm going to go B below 5. So this is 5 minus A, and this is 5 minus B now. Yeah, coming this way. And then what I'm going to do is I'm going to draw a pair of overlapping rectangles. I'm going to draw this rectangle like this. This rectangle here, which has an area of another area of 5A, you can see it's just the same as the one above it. And then I'm going to draw this rectangle here, and that whole rectangle has an area of 5B, just the same as the one to its right. But of course, what I've done is double counted this. And so therefore, because I've double counted it, I need to take it off. And that bit there is A times B, so I need to take it off, minus AB. But of course, that cancels perfectly with that. So if you like, these two areas, the fact that I'm double counting this here perfectly negates needing that. So in fact, what I'm doing here is moving that into there to complete those two rectangles. So now I've got my 10A and my 10B, or my 10 lots of A plus B. And the question is, what's left here? Well, if we have a look at this, to get this length, we're doing 5 minus A. And what did we notice back up here? That 5 minus A is C. And similarly, to get this length, we're doing 5 minus B. And what was 5 minus B? But D. And so this area is CD. And so we've got 10A plus 10B plus CD, or 10A plus B plus CD. And I think that diagram is an absolutely lovely way of seeing why this hack works, because basically we're taking that product and we're chopping it up and rearranging it into different parts, and those parts just so happen to be able to match what we're doing with our fingers absolutely perfectly.